Well, good morning, everyone. This morning we're joined here by some dear friends that we've gathered here. Some might say a renter crowd. Um, looking at themselves, there's probably views of views. We've got a big screen set up, so they're quite occupied there. Today we're going to talk about water and the water layer and all that we've got going on there. And I'd like to welcome our team here from this property at, I don't know how to say this, is it Myocum? Myocum. But they're all Victorian, apart from a gentleman here from France and a couple of from Kiwi and a couple of others. So we're all Mexicans on a journey, so to speak. So I've come up here to help with some mapping, as I told you all about this morning, and she'll be here for much of this week and catching up with a few people, including Blair, who's not on the call at the moment, so he must be on his way over because he's very close by. Right, well, with water, let's have a look at that. So I'll just move this out of the way. Whoops. Okay. What can I do? I can make it smaller. Right. So how's that screen size? Pretty good. And I hope it is for you at home as well. So this week with water, big difference to what happened with our last program was the production of this chapter of the Regrarian's Handbook. So those of you out there in the living room, we have this book called the Regrarian's Handbook, and it's 3 chapters of 10 in. So, and to give you an indication, this is the first 2 chapters right here, and that's the 3rd chapter, water. So it shows you how important water is as a topic. So we'll be going through that today, and that will, of course, be the primary text for this week's work. The other primary text, which I'll just touch on for a moment, is The Challenge of Landscape by P.A. Yeomans, which was written in 1958, and you'll find a copy of that in the Google Drive. I think it's here. Let's just get a copy of that. The Challenge of Landscape. Yep, so it's there. I'll put a link of that up there. So that's the download that we took from the soilandhealth.org website, which was authorised by Alan Yeomans to make a digital copy of that book. It's my favourite book on keyline design. The other piece that I wanted to refer to was the chapter 11 of the Holistic Management book, 3rd edition, which is titled The Water Cycle. So take a look through that when you get a chance as well. Well, I was a bit unsure about how to deal with today, given that now the Regrarian's Handbook has been, or the water chapter has been finished, and so I'm going to look through that, but I'm also going to just look at some of the stuff that I had that was outside of that from our normal sort of rec slideshow, and start off with capturing something that's really important, which is volume. Now, a lot of people don't understand or appreciate that, appreciate the principle of volume. And when you're talking about the water layer, a lot of it's got to do with this principle. So here in the 51st state of the United States, we use metric. So we used to use another method that both the UK and the United States use. And so it's very simple. So 1 millimetre of rain or any thickness of material on 1 square metre equals 1 litre of volume. Now, it may weigh different amounts according to its specific gravity, but it's the same volume. 200 millimetres on 1 square metre equals 200 litres, and a lot of people would associate 200 litres with a 44-gallon drum or a 55-gallon US gallon drum. And then if you've got one of the IBCs, they're about 1,000 litres. Well, that's 1,000 millimetres or 40 inches on 1 square metre equals 264 gallons. Why is that important? Well, here I'm standing with a couple of people on the northern um, slopes of an island called Lanai. Now, Lanai is the largest of the privately owned islands in the Hawaiian Islands, and it's owned by a guy who owns a big yacht and might sail up and down here. His name's Larry Ellison, Oracle. So a lot of people use his software. He's one of those many high net worths in this world who are buying places and then sort of rejigging what I call baronial feudalism. And there's a fair bit of that going on. As the price of land increases, so does the fact that the only people who can generally access better quality land in better districts off scale are high net worths, medium to high net worths. And so we're getting a sort of almost a cycle back to the kind of land ownership systems that many of us escaped, or our ancestors escaped in Europe, and so on. Now, one of the things that happened here was, which is why I'm standing here with some Indigenous people, is that when this property was, let's just say, garnered in about 1926 by a relative of my own, Mr. Dole. My mother's a Dole, so I'm a Dole as well. You know, Dole bananas. That's why I'm trying to give them up feather. Too many bananas in the system. When they took this landscape, only 2% of it was still was able to remain in Indigenous hands, but 100% of the 96,000 acres of this land are functionally eroding. And what that means there is that, and this is what I was talking to these people about, was, well, we were looking at the soil surface and seeing how much soil had actually been lost in a really short period, just like in the last year or two. And we found that in many cases, 10 to 15 millimetres of soil had been lost in 1 year. And what was the concern for them of that? Well, turtles were finding it very difficult to swim to shore because they were wading through the really turbid water. So the water was thicker. So it had just as many litres of water, but it was now mixed with the mud that was sliding off these slopes. And so they were fatigued, losing, and in doing so, having declining conception rates, declining fertility rates, and so on, and being easy prey or easier prey for prey animals that happen upon them. And it's all a function of this landowner who has, you know, conceivably all the money in the world, not taking care of their landscape and not making decisions about covering their soil. And that's one of the biggest things that we talk about is the power of this thing here, the power of the raindrop. That's a high-speed photograph of a raindrop hitting a bare soil surface. And why that's important to us, many of us over time would have found ourselves doing soil tests where we get a jar, like a large jar, and you'll put some soil in it and then shake it really hard, and then you let it settle out. Well, that's ostensibly what happens every time a bare raindrop hits a raindrop hits a bare soil surface. You get a separation of particles, clay, silt, sand, and organic matter, and then they all settle out when they all land. And the particles that are the smallest rise the highest, and they're the last ones to land. And so what you get is what's called surface capping. The sun comes out, dries the clay, and then it rains again and you get increased runoff and flooding. And that's happening all over the world as we practice bare soil agriculture writ large across the planet. So it's something that's really, really important. And if here we are in this beautiful part of the world on the northern shores of New South Wales, very special place, and where the ocean is very important to people, as the ocean should be anyway, but they're particularly important to people here, and yet people still practice agriculture that murks that water and reduces its quality. In places like the Great Barrier Reef, this is an incredibly large problem because this soil, it's mobile, is mobile with lots of other stuff as well. All the agrochemicals that people use and the novel compounds and all of the organic compounds that people use as well that are mobilized, which then go and pollute the reef. So it's really important to understand volume. So I'd like us all to hold our fingers together, our finger and our thumb 1 millimeter apart. Right. Now, it's really hard to do that for a prolonged period. I know there's some Zen folk up here that can probably manage it quite well. Something you might want to practice for yoga in the morning. That 1 millimeter on 1 hectare represents 10,000 litres of soil if it's soil lost. All right, so that's 1 hectare, which is only 100 metres by 100 metres. It's a really tiny, almost imperceptible paper-thin sheet of soil. But when it's lost, you take it all, put it all together. That's 10 IBCs. Right? So it's an incredible amount of soil. But the flip of that too is that if that soil is covered, then and you get 1 millimetre of rain, and that's 10,000 litres that are being potentially absorbed as well. So it's really a choice that you make when you cover or uncover. And I think that that's really fundamental to any discussion around water. Because a lot of people talk about different structures with water, and they talk about, building swales and dams and keyline systems and all sorts of stuff. But really it comes down to this. It comes down to, is your soil covered? And the mantra that we generally have is that, as far as the answer to that is, that your soil should be 100%, there should be 100% ground cover 100% of the time. And if we have that, then things will be very, very different. So I just wanted to, I think I'll go straight to there. Just bear with me. Where's that? Yeah. So the water chapter. Took us a while to generate this. Now, I'll just go through the sections so that people are familiar with these. So what we did was, when we looked at the design of the water chapter, because the other part of, as many of you will know, the other part of the Agrarian's Handbook is that it's our pedagogy. So it's our textbook for the training of people in regenerative agriculture or regenerative living. And so we created a range of categories. And as always, we start with the enterprise context, because it's always important for you to understand your own context and that of your enterprise before you start considering what to put, what to do, what to put where, what to invest in. So we've got that. Then we look at the categories of water, and then we try and have an understanding around hydrology from the perspective that some of the perspectives we've just discussed. Look at quantity, quality, the control of water, sources of water, where do we place storages. Have quite a big discussion on small earth dams, because a lot of people are doing those and are interested in them and don't do them well. So that's important that we talk about them. We also talk about tanks and treatment. And then after that, we talk about reticulation. So how do you get water around? How do you irrigate it when you do get it around? And then how do you look at fire protection and restoration? Because that's the other thing that water does. Uncontrolled water on uncontrolled landscapes or unmanaged landscapes create a whole range of erosion issues. And then we've got the usual formula and appendices, etc. So let's just have a look at some of that broadly. So P.O. Yeomans, one of the things that he said in a video, in an interview on ABC in 1979, is that water is the principal planning medium. Water comes before roads, and fences and everything. If you get the water right, you get the roads right, and you plant the trees in the right place, and no one does that. Saying no one does that apart from Keyline at that stage, Keyline being a precursor to the permaculture design and so on. So he felt about it in that way. Interestingly, I'll just read a section here. I did this. I went and did it. I was working in Vietnam from 2004 to 2007 and living over there. And I came home and Bill Mollison caught up with me and he said, "Oh, you should come down and do this PDC that I'm doing down in Melbourne at the Melbourne University." So I went along and listened to that, and Jeff Lawton, who's from this region, he pointed me out because he and I had known each other for a long time, and pointed me out to the participants, saying that we were both reconstructive earth surgeons. And I sort of nodded, and I hadn't really heard of it in that sense before, and I was a bit troubled by it. And I was in the midst of a large earth moving project there. We moved over 3 years, about 1.5 million cubic meters of earth. So it was a pretty big project. So I've moved as much earth as pretty well anyone in this sort of permaculture, regenerative agriculture movement. Anyway, I sort of I reflected on this after, and it really the statement started to ring in my ears, particularly when I started to consider holistic management which is another methodology altogether. And particularly when I started to think, am I working on the cause or the effect? And I thought about it from the perspective of, and I was teaching in California, and when you teach, sometimes you just I don't know, you just stuff comes out of your mouth, and I was talking about this topic and how I was troubled by it, and I said, it's like plastic surgery. A lot of people, when they get to a particular age, they feel like they need to make adjustments to themselves to remain young, or to remain to sort of create a visage of that denies reality and gravity in some cases, and I thought that from the perspective, I was thinking, because I often think in analogies, and I was thinking of Mother Earth, and I thought, well, she doesn't actually need reconstruction as such. We keep talking about it, we keep doing it, and humans have been doing reconstruction. We've built roads and done earthworks for thousands and thousands of years, and they outlive us. And when we understand the Keyline scale of permanence, well, it's the second tier on the Keyline scale of permanence is land shape. And when you adjust the land shape, it doesn't change. So, when we're all pixie dust or whatever we become, a lot of the things that we do in terms of earth forming will still be here. Like if this house was destroyed for whatever reason and never came back, well, then you come back in 100 years and you'd still see where the house was. You'd still see the swales, the dams, the roads, all of these different things. It particularly struck me when I went to Rome for the first time, and I saw one of my favourite movies as a child was El Cid, and there was the Circus Maximus, which was a chariot racing, and someone apparently died in the movie, but that's another story. And I went to the site. I said, I've got, everyone was in the family saying, I want to see this. And I said, I want to go and see where El Cid was made, Circus Maximus. So I went there, and it was sort of like this abandoned lot in the back streets of Rome, and completely neglected, except for the beautiful marble stairs for when the chariot drivers or the emperor would walk down, and the earthworks, the batters, and the track were still absolutely perfect. You could have done a little bit of work to it and started chariot racing there next week. But it really struck me that when you're doing earthworks, you're doing it it's really permanent. And the other thing that struck me was that, especially again from holistic management, was that You, when we plan, most of us, when we plan around the environment, so there's a rule in the holistic management feedback loop, which is that you plan assuming that you're wrong with the environment. And humans being creatures of hubris, we tend to, not humility, we tend to plan assuming we're right all the time. And that's why I have a problem. I didn't say this yesterday, but I will say it today. I have a problem with master planning per se as an approach, because it tends to think that we've got things right, as opposed to being incredible. And that's one thing I've learned over my journey of nearly 30 years as a farm planner. That's why I've even changed the term of describing myself from a designer to a planner, because a planner, design suggests that you've got things right. Planning assumes, well, from the way I look at it, that you're actually planning and you've got feedback involved in that, and it's a much more iterative process rather than thinking that you're some omnipotent creature who's going to be able to foretell all of the things that will happen as a result of what you're doing. And that's, so I'm a very cautious designer and planner as a result of that, and I've become increasingly cautious. So, as I've said here, Mother Earth doesn't need reconstruction, which is what I sort of relayed in this talk in California. That what she does need is maybe a little hydrotherapy, a gentle massage, perhaps some acupuncture, or a dietary change and some rehydration, as opposed to permanent scarring, because we do see this all of the time. And as I said here, permanent scarring is heroic and impressive to some, and it expresses domain, which of course we were given domain, weren't we? It gets shit done. And that's a hashtag that's out there. You've got to get shit done. Well, I put the emphasis on shit, because you're getting shit done if you're not being due diligent and you're rushing ahead and so on. So we think that if we're going to look at Earth moving, because a lot of people, when they think about the water layer, they think about Earth moving, particularly those who've had any permaculture training or keyline training or even landscape architecture and so on, soil conservation as well. It's all about earthworks. And I'd like people to just take a bit of a chill pill on that and ask, how can I assist the site and this landscape to better accept and hold water? Accept water, right, for all of what that means. How much water do these people really need for reticulation and in storage? Because often we build things that we don't need, they're superfluous. And as is a topic throughout the Rex and throughout our work, we're always talking about capital overreach, and how most of us have only got a limited amount of capital, or relatively limited amount of capital, and you don't want to go and use all of that capital up on stuff that perhaps is not necessary, or that you think is right to do, but you haven't actually studied to see if that's what you need or what's needed for your system. And do I really, really need to move this earth? Because if inappropriate, the impact is considerable and expensive, and like inferior plastic surgery, an obvious, expensive, regrettable, and permanent disfigurement. So I think I've made myself fairly clear there. So the other thing to consider, again, as we've done with other chapters of the Agrarian's Handbook, is to consider the sort of flow of it all in how one is going to build a layer. So for a start, water is heavily regulated. And there's differing views as to how appropriate that is. From our perspective, some of the policy settings are good, some of them perhaps are not, but that's policy. But you need to understand what the rules of the game are. So you might say, in the application of the Agrarian's platform, where we will say, what's the climate? What's the regulatory climate? Well, it pays to understand that, because if you don't and you go and do things that you aren't allowed to do, then that can bite you on the arse. It's really helpful to understand the catchment hydrology that you have, so that you can see how your system fits within the whole, within a whole watershed in particular, because everyone's part of a watershed, and it's really important that if we're going to develop, as my friend Brock Dolman calls from the Water Institute in California, basins of relations, then it's really important that we develop a very much a watershed-based consciousness as far as our catchment ideas and work is concerned. What are we doing about quantity and quality? So you will find that you have different quantities of different quality of water available to you, and how much of that do you need for different uses? So that's something to think about securing, and how secure are those sources. The control of water. As I say here, it's very rare to find a site where the capability of that site is perfectly suited to the land use that the planner is looking to impose. There's very few class 1 sites, as it were. So its drainage characteristics are often a blessing and a curse, controlling drainage so that it is increased or decreased is often the work that a lot of people are doing. And this site that we're on here is no different to that. Different sources of water. So what are the varying sources? And that relates in part to the quantity and quality. Where are we going to store it? How are we going to treat it? How are we going to get it around? What are we going to do about fire protection? Because a lot of people find themselves living in fire-prone environments. And so how can we consider those parts? And then what are we going to do about restoring any areas that require that? So let's proceed from there. So if we look at the regulatory frameworks, the first is to seek out agencies that regulate, there you go, there's a typo, that regulate water access. So you might start with doing that in a sort of a quiet way, particularly if you're interested. Look, it's one of those things as it is with any planning. If you go down to the local planning office and declare all of your cards all at once, then you might be compromising yourself a bit. So you do have to, as Paul Corregino, who's on the workplace, says, Corregino, pardon me, says we have to understand the ecology of government better, or as well as we can. And so that's part of these regulatory frameworks that we've discussed in Chapter 1, where we're saying, look, get a sense of what the vibe is there, and how far you should or shouldn't go with putting all your cards on the table. But also realise that a lot of stuff is on the internet, and so find all of the stuff that you can, or hire somebody. And a lot of you are not going to be in a position financially to hire people, planners, so you're going to have to spend a few nights on the internet printing it and print out a few things, and so that you can get a strong sense of what the regulations are. And then once you've got to a point where you better realise what you want to do, then you'll go through a process with any field officers and those that are policing things. Right, now I'm just going to change this view to 2 pages, I think. 2 pages, yeah, there we go. So this is where we sort of shift into the keyline stuff, because so much of our book is built, well, it honours and you might say extends on the work of the great P.A. Yeomans, and of course our Regrarians platform is based on his 1958 keyline scale of permanence. So we have to, and there's so much sense in keyline that still persists today, and so many insights that Mr. Yeomans had. One of those was looking at the categories of water. And what we've done in this diagram and others is to also try and consider where we are in a landscape and what kind of not only what category of water that we have, but also what stream order or what order of flow are we a part of or managing at any part of our landscape. So within the landscape, there's 4 categories of water supply available. One is absorbed rainfall, and that's the highest quality and the lowest price. And it's one that often people overlook. And as I mentioned before, you know, that 1 millimetre of rain on 1 square metre equals 1 litre. So take that out to a hectare, that's 10,000 litres. Now, what happens if we improve the climate of the soil such that we have management which increases the soil carbon? Well, every 1% increase of soil carbon in the soil equals another 168,000 litres of water able to be held in the soil per hectare. So when you get into soils which have a very, very high carbon content, they're basically raining. And that's why I think there was a post this week by somebody who said that they'd found that they had C4 grasses. So we've talked about C3 and C4 plants before, but just to recount on that, C3 grasses are those that are what we call C3 plants, cool season plants. Typically they are actively growing when there's humidity, but in a cooler part of the year. And then there's C4 plants, which are incidentally more efficient at photosynthesis, so use less water in photosynthesis, and they typically grow, they're called warm season plants, and they're a lot of the vegetables that people grow over summer, but they're also summer grasses, summer pastures. And those plants are green over summer or in the warm, so they're warm season plants. Now, if you live in an area which is has winter dominant rainfall, and typically in those parts like California, southeastern Australia, southwestern Australia, the Mediterranean, so Chile, the Mediterranean itself, and so on, South Africa, all parts of South Africa, then if you see any grasses that are growing in summer and they have a thick leaf, a wide leaf, then that would probably tell you something about the soil. Because there's no rain, so how's that plant able to photosynthesize if it's not able to transpire water out of the ground, if it's not being irrigated? Well, it's coming from the soil carbon. And so what we find, and what we found over time, is that as people in winter rainfall areas have increased their soil carbon content, so too with that has been an increase in the amount of green vegetation that grows over summer, even though there's no rain or there's very little rain. And so that's something that's really good, and it's a good fire control measure because green landscapes are less fire prone, but it also means we're more productive. It also means that we're pumping more carbon into the soil, because whenever you have green leaves, then of course you have sugary exudates coming off the roots every day. And they're all pumping, as Christine Jones called them, Dr. Christine Jones called them, liquid carbon into the soil, polysaccharide exudates, which are feeding the soil mycorrhizae and other soil microorganisms with the economy of life that is largely driven by photosynthesis. So really important that we focus on trying to get as much absorbed rainfall as we can, and the best way to do that is to have 100% ground cover 100% of the time. Another source of water or category of water is runoff from rain falling on the farm. So there does come a point where a soil can't take any more water, and so you get some runoff. And poor design and poor management will actually accelerate runoff, and you'll have less control over the water in your environment. So that's an important thing to try and harness where you can, so that we can manage that. We're looking also at external sources of surface water. So a lot of people who are irrigators in particular are usually downstream. as it were, and lower in the landscape. And they get water flowing onto their farm via rivers, creeks, channels, and canals. And then the fourth category of water is groundwater. In a lot of parts of the world, this is one of the most commonly accessed waters. And of course, it's declining in its volume, primarily because of the decreased infiltration rates that are occurring all over the planet as a function of our destruction of soils and our uncovering of them. So it's really important. And the other thing that's happening with groundwater is, of course, too, that we're getting gross amounts of contamination from the novel compounds which are soluble in water and leach into those water tables. So nice stuff to be contemplating. All right, well, I'll just touch on this slide here, this page here for a moment. It sort of moved on from where I was talking before, where you've got sand, silt and clay and then organic matter. And what happens when that raindrop hits? So you get this little minor explosion but all of these raindrops all gather together because they're not falling in isolation. And what you then get is what's called detachment, transport and deposition. And that's a natural part of the cycle of erosion and deposition. But if it happens all of the time, then that process accelerates, and that's a problem. What also happens is that we get this surface capping. And so all those finer soil particles settle, sun comes out, we get a terracotta surface, as it were, and especially in countries like Australia where we've got very strong sun, especially in areas like here and further north where the sun is quite high in the sky for a lot of the year and it's quite strong. So you get a lot of runoff. And in summer rainfall areas, which is where we are here today, a lot of the United States is summer rainfall. Lots of parts of the world are summer rainfall. And what we get is lots and lots of rain, which comes at very high velocity. And this is an interesting point, that we previously thought that the sheet wash or the flow of water over the soil was the most destructive. The kinetic energy of a moving object is equal to half its mass multiplied by the square of its speed. So as water droplets grow in size, and I add to that in temperature, because here in the subtropics and the tropics, the water temperature of rain is higher. And just as an aside, if any of you have dirt on your hands, and you can try this after you've worked today, any of you got dirt on your hands, especially clay, go and wash your hands under cold water and then go and turn the water up till it's warm and see the solvent action, the increased solvency that increased water temperature has on the dirt that's on your hands. Right? Try it today maybe with cold, tomorrow with warm, and the next day with hot. And that's the effect that rain has as it increases in temperature too, which is a function of climate change or just where you are. So a lot of areas which get summer rainfall get intense rainfall, and as we know, it appears that rainfall intensity is increasing, so therefore droplet sizes are getting bigger. And so, so it's just like this ongoing problem that we have that's not often talked about. People talk about all sorts of other things, but don't necessarily talk about this really serious issue. So the mass of a 5 millimeter diameter raindrop is 125 times greater than a 1 millimeter raindrop. Would someone do me the honor of getting me a glass of water, please? Thank you. So, yeah, and a lot of because of a number of other factors, a lot of clouds are getting pushed up higher and falling from a greater distance. So rain is falling from a greater distance. So rain reaches terminal speed and increases in terminal speed. So that's a really big problem. Okay, thank you so much for that. Cheers. Okay, now where is water in our landscape? So a lot of us will be looking and going, all right, well, I want to do different things. I want to see, and we were talking over dinner last night, a few of us, about reading the landscape and reading it for water and reading it for its hydrology. And one of the best things to do there is to read plants, I find. Plants, it's one of the important reasons why a lot of us should engage in a much better understanding of the plant kingdom, because the one great thing about the plant kingdom is plants don't move. Or when they do move, then you know you really got a problem, right? They only move when they reproduce. And so if you've got the incidence of plants and you've got incidence within particular plant species of particular characteristics in terms of form or in terms of disease, then that can tell you a lot about that landscape. And you don't need to know, you don't need to know necessarily the species. You can just understand the genre or the plant family. Because if you just stick at that level, if you're traveling a lot and you're looking to do, or if you're looking to understand the plants on your own property, well, then it's useful to get that kind of knowledge. So understand which plants are indicators of reliable water, for example. Now, I think I'll just check who's on the workplace this morning. Where are we? Is the Zoom thing on? Because I'm on my... I don't have Sam and Ray on here. But Sam and Ray, when we went up and did a program with them earlier in the year, we were looking to position a dam because they've got a market garden and they need to increase their water security. So we're looking at a place, and we're in this one place, and I said, this has got to be a really good spot because there was tea tree everywhere. So there was melaleuca, and this particular, a lot of melaleucas, especially the paper barks, heavy paper barks, indicate that there's a reliable amount of water. There was a lot of cyperus there. Cyperus is a type of rush or wetland plant. So that was there. There was also juncus and a few others there. So knowing that those species were there meant that there was a pretty good reliability now from a planning perspective of saying, yeah, I think this is a good spot. We should proceed to the next process of investigation. And so that's apparently what's going on there. We can also look at contorted trees in a forest. Contorted trees, Sepp Holzer, the famous Austrian farmer, and now farm planner, I suppose you would call him, farm developer, he will often look for contorted trees as in any part of a system. Because if you've got generally good form, and then you'll see in one native tree there that it's all contorted, then that will probably suggest from his observation and others that there's underground water right there. And because it's creating some sort of imbalance in the mineral supply to that plant, might be a little bit more acid there or so on, and then that creates a variation in the form of that species, which is interesting. Just like it does with us, my ancestors lived in Ireland, lived in huts where if I walked in them, I'd bang my chin on the door because they were so short, because they lived on peatlands where their diet was pretty poor because it was compromised by living in a highly acid environment. And so the range of vitamins that they were able to get, and because they were poor as well, meant that their nutrition was low, and they probably had really bad teeth, and they probably had double rows of teeth and all sorts of stuff as a result of having fairly poor nutrition, particularly as a child, and so on, and in their development years. So whereas I've had the benefit of growing up on a farm with lots of raw milk and highly varied diet and ferments and all the rest of it, so my teeth are pretty good, and I'm 6 foot. So there's all of those things that occur in lots of different ways in all kingdoms of nature. So you can pick those things out. So that's useful. All right, I want to shift on to something that now Yeomans again did, and this was In permaculture, there's a discussion on permaculture zones. So there's 5 zones, depending on which school of thought. So the original zones of permaculture, there were 5 zones, and they were all related, as we talked about, I think last week or the week before. It was last week, yeah, in terms of the relative ergonomics of, as I put it, of interaction with particular landscape schemes and landscape management themes. So Keyline, Yeomans, when he wrote his last book, the City Forest, which was, and the subtext of that was the City Forest, the Human Environment Revolution, or HER, as he called it. In Chapter 6, Design for the Environment, he referred to 4 different zones within water lines of a completed keyline plan. Now, my late friend Geoffrey Booth, who died a couple of years ago, was a very great scholar of keyline design and bequeathed to me his keyline archive, which is the most substantive keyline archive that anyone knows of, we think. He, through his work, through his scholarly work as a chemical engineer and geomorphometrist, that is the person who, geomorphometry, as we introduced to you before, is the study of landforms. In that work, he expanded on what Yeomans had sort of only almost referred to in passing, and so we expanded that when we worked on Geoffrey's animation, the Genius of Keyline, which you saw earlier in the program. So within that, there's 4 zones in a keyline landscape, and one could look at any landscape that's developed completely as having these 4 zones. So let's just look at those. So you've got the catchment zone, which is the area above, which is below the main ridge of the landscape and above the highest water conservation channels. The retention zone, which is the area between zone 1 and the irrigation channels. The irrigation zone, so that's the areas of land which can or are irrigated. The reconstitution zone, which is the areas that are below the lowest boundary of the water irrigation zone and any secondary valleys. So let's have a look at what they might look like. Oops, hang on, let's get that smaller. So this is one of the plans that we keep using in the Agrarian's Handbook. This is Area D. And you can see here the black line around here. Sorry, the pages aren't together. But the black line there, the thick black line, is the main ridge line. And then the dashed line here, as you can see from the legend, is the primary ridge. Then we've got the primary valleys, and then we've got a secondary valley, and so on, and then we go off the property. So that we're saying that black line is also the perimeter of this property. So you can see in the case of this particular landform that if that zone 1 is actually a fairly dominant part of this property, and then zone 2 is a fairly small part. Zone 3 is actually bigger than zone 2. So as a result of a large zone 1 and all of the water that's harvested from that, we're able to irrigate quite a reasonable amount of land by gravity from that system. And then we've got a relatively small reconstitution zone, and then there's final dam before it leaves the property. Now, that's an imaginary, because we had never been to this property. We just chose it out of the blue to use as an example in the handbook, but it just goes to show. Now, this is just something we're using to show. Now, this is a property that Yeomans himself developed and still exists largely in its entirety now, after it was developed in the 1950s. It's called Nevallen. And it was sold in 1964 to pay for the death duties following the unfortunate death of his wife, Mrs. Rita Yeomans, in that year. So you can see in this property that the proportions of the zones are quite different, and that's all to do with the different land shape that exists here. So it really does show you that depending on that the shape of your land will provide a range of different opportunities when applying the keyline plan in its full extent, which is what's happened here. So just as I applied the keyline plan in its full extent here, you can see that there's quite a large area of catchment zone which is only available for catching water, not for actually harvesting or reticulating that water, unless we pump to it, right? Whereas this property here, you can see that there's only a really small area of zone 1, even though the main ridge line runs along there, and a lot of it is irrigated. So and this is one thing to consider, particularly if you're looking to buy a property and you want to develop it following these principles, and I'll say develop it along the principles that you're trying to use gravity as the primary means of distributing water on your property, then understanding it and reflecting on it in this way is a very helpful way of saying, all right, because when you buy land, every square metre of it has the same price, but if only 20% of it is useful, well, that's made that very expensive land versus land where 80% of it's useful under the terms of what you call useful. So if you can then apply another layer of thinking to that, where you go, well, gee, 80% of it is able to be irrigated by gravity, then you're really cooking with gas, right? That's or irrigating with water, I should say, right? So that's something to consider again when you're planning, and when you're looking to purchase property. Is, am I going to create am I getting into an environment, a landscape that's going to be dependent on fossil energy or photovoltaic panels or some form of energy and motors and entropy? Am I inviting myself into that, or am I getting into a situation where I'm going to have the most reliable thing that we've got, which is gravity, right? And where I can put in solid state systems which which have very few moving parts, and where entropy is something that's probably way off in the ether, right? If we ever have to worry about gravity stopping, well, then we've all got a pretty big problem. So, all right. I don't know. Now, I'll move along and just do a bit of because I don't want to go through every page too closely, because I want you to have a bit of a read of things. But there's a few principles that we've tried to put in here. It was a good friend, Brock Dolman, who introduced to us the concept of anandromous and catandromous drainage. It was an interesting discussion that we had. This is probably 12 years ago or so now. So Brock came up with this concept called, as part of his work with the Water Institute, which is at a place called Occidental Arts and Ecology Center in Occidental in California, in I think it's Sonoma County, just north of San Francisco. And so the concept here is that within the idea of the basins of relations is that even if you're downstream, there are organisms, and I didn't think about this until he was talking to me in these terms, but even that when you're downstream, there's organisms that go upstream and they move nutrients upstream. And when they're not just moving nutrients. And I talked with David Holmgren, my friend, about 20 years ago about this on a different topic. We were talking about cockatoos, and that cockatoos, he'd just been talking to a CSIRO scientist, and this scientist described a cockatoo as mobile nutrients. That it was because it is, its body is made up of nutrients. It takes nutrients from one place and then it flies somewhere else and deposits them. And then ultimately it deposits its life. It deposits its body somewhere. And that might be well upstream from where a lot of the minerals that were deposited in its body over time were collected from. And so when we think about that, it starts to, well, I think it, well, for me at least, it started me to think about, again, that basin of relations approach, and that water, how we are part of a watershed, and how important it is, because a lot of people who are down right on the coast, they're thinking about people up the hill as being people who, or managers or systems, is that everything is coming at them. You know, what you do up there, I'm very, you know, you need to take a lot more care of your catchment. We see this in the Murray-Darling Basin debate as well. People down on the coast are the surfers and all of these characters are all, and people who are involved in marine biology and even, are very conscious of what's happening uphill, right? Because water comes down, it brings nutrients, etc. But what about all of the other organisms that are interacting with the nutrient cycle, right? Nutrients don't just flow in water, they fly, right? So they fly in the air, they fly by dust, but they also fly by organisms. And so if we've got that seagull that's down here that's eating your shit down here because of your bad practices, but it's okay because, you know, they did it up there. Well, what's happening with that seagull when it goes for a bit of a flight up there? What happens with the fish who have different cycles? And also so some species are born in fresh water, migrate to the ocean, get fat there, then go back upriver and spawn and sometimes die up there. Salmon are a great species of that, to indicate that. And then you've got the catandromous cycle, which is species which are born in fresh water, get fat in fresh water, and then go back out to the sea and die or spawn, like eels. So another part of the thinking of this is us contemplating why it's important for us to not dam rivers, and for us to not put dams and barriers across particular stream orders. And you start to appreciate why that's important, because you start to adjust these incredible, you know, these are well-developed cycles. You know, humans have only come along with our little interventions in the last 20, 30, 40,000 years as thereabouts, and particularly the last 200 or 300 years into the industrial age, where we've really ramped all of these interventions up. This stuff is very mature technology, biological technology, and there's a lot of disruption that we're causing without really knowing what we're doing or the consequences of. So it's important to understand. If I talk about, hang on, what's going on here? Oh, here we go. I think because it's doing that. Single page. Okay, another thing to consider if we might move into quantity, so after moving out of hydrology, is a really important question to me, and I touched on this earlier. So the main concern is to balance the enterprise water needs with water availability. In addition, consider the future needs of a site and how these will be met. So will your carrying capacity, and you could look at that in any, you know, whether it's whatever you're talking about, will your carrying capacity increase and to what level? So you've got to do a little bit of forecasting here. What volume of water will you need as any orchard trees that you're growing mature? Because they have increased leaf surface areas, and so that leaf surface area is going to increase the amount of transpiration, which is going to increase the amount of water required if you're in areas where you don't have reliable rainfall and you want to have economically viable yields. Will you expand your project to include systems that will need more water? What capital do you have access to, and how progressive will you be in developing water infrastructure as your capital and cash position changes? And how secure are sources within as well as outside of your control? Because that can change too. So when we contemplate our plan, well, when we look at those questions when we're planning, then that's going to obviously influence the way we plan quite heavily. And then in this section, we're going to deal with, I won't deal with them all, but we're going to deal with human, plant and animal systems. And then within human systems, potable and non-potable systems. So one of the things that's pretty well established now from horticulture and horticultural science is something called crop factors. And crop factors are, if you understand crop factors, particularly when you're at the planning table, then you're just using generally available climate data, you can then estimate how much water you'll actually need for your crops. And not just to make them grow, but to make them thrive. Because a lot of people who are involved in commercial production are interested in thriving plants, not struggling plants. So it's a very big difference to, a lot of people who have let's say a lifestyle property, they don't care. In fact, they don't mind not having such high levels of production, because when you have really high levels of production, you've got to deal with it all. Right? So you might want to back things off in terms of yield from a yield perspective, and you're okay with that. But if you're a producer and you've got mortgages and wages and everything else to pay, then of course you want to up production, and so you want to understand what the crop factors are, so those plants that you're growing produce as best as they can, and that water availability is not a substantial limiting factor to that. So with that, we look at the irrigation requirement equals the reference evapotranspiration times the crop factor minus the effective rainfall. And so we've got an example of how we calculate that in here. So we've got this example farm here. We've got the available pan evaporation figures from the government, from the Bureau of Meteorology website. We've created from that a pan factor, which I've got a reference to there, and you can read about that later. And so what we've done is we've created from that pan factor and a reference evaporation rate that's going to occur in any given month. Now, there are programs which do this, which are linked into your weather station, provided your weather station is appropriately equipped. And so you'll get live figures on what the actual crop factor will be. So you can certainly go to town on this. And then you look at your total rainfall, and then from that is developed what's called the total effective rainfall, because the effectiveness of rainfall is dependent on, because you might get what you think is reasonable rainfall, but then your plants have actually used up or there's been excessive evaporation that month. And so what you think has been effective has not been at all. So you've got to be that's really interesting. I was at an old client and friend's property a few weeks ago, and he had a really interesting way of dealing with this. He's in a fairly humid part of Australia, and he created his own. I'm still trying to get my head around the efficacy of this, but just hear me out. He had a normal rain gauge, the ones that are about 100 millimeters in diameter, and they've got a tube like that, and then they've got another tube inside. Do you have one of those here? Or something similar? So you've got that. Otherwise, you've got a rain gauge which is like on a slant. A lot of people have those too. The better ones to have are the ones with the tube inside of a tube. So anyway, he had one of those, and he never emptied it, which I thought was curious. Those carry about 200 millimeters of rainfall, so they'll do a 200 millimeter rainfall event. And he said, oh, we don't get that sort of rain around here. And I thought, that was curious. Anyway, but what he was doing daily measurements of the increments of increase or decrease in that. So he was basically using it as a poor man's evaporation pan. And from that, over, I think, about 10 or 15 years of taking these figures, he was looking at that and his soils and was sort of deducing these patterns as far as when he should irrigate and when he wouldn't. And he got it pretty right. So it was interesting, and that's one guy up in the woods who's just sort of working things out, and it got and it was fine for him. So I just thought I'd share that anecdote with you. But yeah, that was quite interesting to see. The variation on that, of course, is that there is a lot of variation, and that's what we've written here in these tables around the different crops, because different crops have different crop factors. In other words, different crops are more efficient at water use than others. And so that's something that in the math of this, you put in. Now, a lot of people, including at this property that we're at here, grow a wide range of crops. And so that complicates things. And so one will find that you can average things out and get a pretty strong sense of what crop factors there are. But anyway, we've created a pretty extensive list there. So we've given an example here so that if this particular client wanted to grow walnuts, if they were planning to grow walnuts, then we've worked out the January irrigation requirement, for example. So we want to know how much water we need for that period. So we've gone through this process and so on, and then we've got to a point where we know that we need about 2.5 megalitres per hectare per year so that we can grow walnuts optimally based on the climate that we have. I did a recent job again at this one up the road here that I was at. It's called Nowendock, and we did the same process for growing pasture, irrigated pasture, and we worked out it was 2 megalitres per hectare per year. Now, interestingly, if a lot of people will just get a book and they'll go, oh, pasture needs 10 megalitres per hectare per year. And so they'll develop a system which will be based on that. Yep, what was the question there? Oh, Scheitzen. Bugger. Lucky I've recorded all of this. Just come through. Oh, damn. No, I've got... Oh, shit. Sorry, dear people. I might have to... Damn. That's what's the problem when I'm working on a small screen like I am here. I can't see everything. Bugger. Shit. All right, well, based on that, here's what's going to happen. I'm going to have to do this all again for you folks because I've gone through an hour without having a screen shared. I'm terribly sorry about that. Anyway, what I'm going to do though for now, because I'm halfway through, I'm going to continue, and I'm going to continue with the screen shared so that we can kick on. And in the meantime, I'll reschedule and probably do it as a blind thing so that you can just watch it as a recording. I'll check to see that the recording off my screen worked in any case. Yeah, what a bugger. That hasn't happened before. All right, well, we'll carry on. Damn, oh well. Not much I can do about it now, apart from redo things. Take responsibility. Right. Good. Okay. All right, we don't see anything. Righto, okay, got it. What a bugger. All right, well, we'll move on. Thank you for all of that and for your persistence. So one of the devices that we recommend people, if they're, again, if you're interested in commercial production, there's one really good device which we've got a do-it-yourself version of, which is called a lysimeter. And a lysimeter can be a really expensive device, like a lot of these things can be, or it can be or it can measure the, or it can be quite cheap. But what it does is it measures the amount of evaporation released by plants, but accounts for that in conjunction with rainfall data. So it's kind of like what I talked about before, but it's an in-ground example. And so if we go to the just go to the section on that in the handbook here. It's on page 314. So just go to that. It's a bugger. So this is a lysimeter. This is one example. We're actually upgrading this one to another one, which we think is better. But this is an example of a system where you can create a very low-cost PVC off-the-shelf sort of system, and that will that lysimeter will then be something that you can use to measure. We've actually got a passive one, this is a bit more of an active one. And that will help you to determine the crop factor more accurately. Okay, so we'll go back to where we were. All right. We'll have to move along given the time. Okay. All right, testing and monitoring. There's a lot of stuff to do there. You'll have to, one of the things that we think that's important is, well, salinity testing is one thing, particularly if you're going to be looking at or dissolved solids for livestock. But there's lots and lots of different kinds of testing that one can and should do. So you need, again, it comes down to what you're actually providing that water to, and then what sort of quality that water needs to be in for that purpose. So, and there's any number of tests that one can do. So there's visual tests, biological, physical, and chemical, and then there's all sorts of tests within those that are going to give you various amounts of analytics. So, or various levels of analysis. So you can read through that to have a check on there. Just get this to be a bit smaller. Where are we? So let's move along because time is marching on. Now, another thing I want to talk about was control of, from the perspective of control, was drainage. So I spoke about in the Q&A on Thursday, Friday for people, a book called Vegetation and Soils, where after reading that book, I completely reconsidered how I should intervene to change a site's drainage characteristics, because it's quite clear, especially after reading that book from Eyre in 1968, that the vegetation communities that exist on a soil have in large part the greatest influence over the drainage characteristics of that soil. So and as we mentioned last week in the Q&A, I've seen on one site where you've got a very young, like 1,000-year-old, literally 1,000-year-old soil with 4 different vegetation communities on it, and each of those different vegetation communities on that same sample provided a different soil characteristic. So when we have soils which are growing trees on them, then typically the soil is quite shallow, and the reason for that is because trees, when they cycle carbon, most of the carbon that's cycled in a forest, in a closed canopy forest, is in the forest litter. And the litter gets continually cycled by aerobic fungi back into the atmosphere. And so you have that litter cycle going up. You don't get a lot of what's called labile carbon deposition. There's not a lot of liquid exudates. And also, trees don't have very high root density. So when you pull a tree up, you look at it and you go, well, gee, there's not many roots. Whereas a grass, on the other hand, has incredibly fibrous root systems. And some of you will have gone hiking and grabbed onto a tree and realised, gee, I shouldn't have grabbed that tree because it hasn't had a really strong root hold. But then you grab the grass and you go, wow, that is tenacious. And that's because it has a much more fibrous root system. So in grassland, so the corollary of all of this is that the greatest agricultural soils of the planet were formerly grasslands and wetlands. Right? And that's because those systems have very fibrous root systems, and they lay down their carbon primarily through root-based exudates, right? And they do it in the soil and at depth. And so, whereas the great forests of the planet, look at the greatest of them all, the Amazon, when you clear the Amazon, you've just got basically a sandbox, because all of the fertility is in the vegetation. It's not actually in the soil carbon, because it's just a physiological fact. So when we're developing systems and when we're trying to influence systems or direct them in a particular way, the kind of vegetation communities that we might have on them or that we install will have a really big impact on the kind of soil that we'll have and the kind of soil characteristics that we'll have. Now that's quite a variation on a lot of the conventional and contemporary thought and orthodox thought of where we come in and we basically change it mechanically, or we go and buy it or swap it out or do all of these different things, as opposed to taking a bit more of a timely approach to it, where you might adjust it by applying some different plant regimes. So some of the things that we suggest, therefore, to intervene with soil drainage is using holistic plant grazing, keyline pattern cultivation, and cover crop establishment, all of which, particularly holistic plant grazing and cover crop or pasture crop integration, all those two uses are both economic uses, so they're not uses where you're not actually getting something back for it. Because a lot of land uses, what you'll do is you'll try and improve a situation, but there's no economic return coming back to you to pay for it. So you're going in that feast and famine thing again. Someone else's feast while you have your famine, right? So whereas what we recommend is trying to have or consider using systems which give you some sort of return straight away, so that you don't eat through your capital pile. Sometimes you are in, and this is what we have on this coast, there's some creek river flats here which are going to be very heavy, and I would say we're probably dominated by tea tree forest and wetlands, and so the soils are very heavy as a result, and hydrologically they're placed to be. And so if you want to grow particular plants down there, you might do all of the holistic plant grazing, and you might do all of the cover crops and all of those good things, and yet still the soil won't do what you want it to do. It won't grow what you want to grow. So you might need to do some mounding. You might need to actually put the soil up into mounded structures so that you force drainage to occur, and so on. And you might need to even go even further than that, as is happening here, although I think it might be a little bit premature, but that time will tell, is doing a lot of actually deeper drainage, putting in permanent incisions into the landscape so that you allow the water to actually drop to that water will run through the profile, through to those drainage channels and run out of the system. That may not be necessary. It may be, but it may not be necessary. Were we to do it just at 2 or 3 years, it's really astounding how quickly things can change on this level. How quickly a soil can change in its characteristics. Now, sometimes as well, we want to actually decrease drainage, like when we're building dams or we've got particular kinds of crops that we want to grow. So what do we do with that? Well, we're actually pretty good at poor drainage. It's something humans have been pretty good at encouraging. And so some of the things that we do is that we'll use glaying. So we'll use animals to compact or wallow in order to do things such as seal dams. We might add clay or invert deeper. So some soils, for example, might have excessive drainage, and so a lot of sandy soils, and I think I talked about this last week, where you might use a keyline plough, for example, or something similar, where you have clay at depth, and you might invert some of that clay and mix it in with the sand that's overlaying the clay, so you now get a sandy clay. Now that material, with the addition of organic matter, will will have a big improvement in its water retention and nutrient retention and so on. So we go through those sorts of processes. In terms of control, one of the things that, well, there's three sorts of structures that are most familiar to people. One is where people build some sort of channel which harvests that water when we get a big flow of water. In Keyline, we call those water conservation channels, and that's where we harvest overland runoff, and there's a compacted bank, and then that water conservation channel has a gradient. Then there's what was developed in the UK, in Europe hundreds of years ago, and then was popularised by the soil conservation movement from the 1930s, and then very much popularised as a planted system from about the late 70s and 80s, and particularly in the 90s, in the permaculture movement, is the swale, which is generally an uncompacted embankment where water is to infiltrate in, and where planted with trees and shrubs, then there's a gross amount of shading that occurs of the channel itself, which only increases the amount of infiltration. And then the other thing that we do to harvest or control water is we build roads. Now, a lot of people don't build roads with this purpose. We do a lot of this work so as to increase the volume of water that's available to people for various purposes. All right, and then we collect off buildings and all of that sort of thing, which a lot of you are familiar with, in a whole range of different systems, in cisterns and so on. And you've got to have all of these. I'll let you read through this in your time, but different systems for harvesting, and do you have dry pipes or wet pipes? Do you have first flush arrangements and so on? And on we go from there. All right, where are we going now? Just because I'm running out of time. We've got 8:23. There's a lot of stuff on pumps and where to pump and how to set up groundwater harvesting systems and how they're best done in there. So again, if you're interested in that sort of thing, I'd invite you to have a look at it. Also have a look at the different types of spring systems and how they work. So we've got a section there that describes the different springs and how they function in our various systems, and then how you might interact with them. Now, I'd like to look now at dams, because I know a lot of people will be interested in dams and how you build them and where you should put them and all of the rest of it. So we've got a diagram here which looks at the main different kinds of dam structures. Turkey nest, which is one which is a non-catchment dam that you deliver water to typically. Saddle dams, which are found in the saddles of landscapes in between two crests. Hillside dams, or contour dams as they're sometimes known, or ridge dams, depending on their relative position, which are dams which are on the side of a hill and generally will need some sort of water harvesting feature to have them fill. And then valley dams, which can just work off the catchment of that primary or secondary valley, or they might need enhanced catchment by the addition of water harvesting channels or swales or the like. And then you've got the last dam, which is the floodplain dam, which is one which is where most of the water is below grade or below ground level. Now, there's three different types of embankments of dams, which is what we've listed here. There's one that's called a diaphragm dam, and that's one of the two most common dams that people build on farms. Generally, we'll use this where there's limited clay of the quality that we want. And so what we'll do is we'll push all of the poorer material to the back of the dam and then, and then put in a clay liner, which will face the full supply level. Next one, which is the most common dam that's built, and often by default because people haven't done any engineering or investigation prior, is what's called a homogeneous dam. And this is where all of the material that's dug out of the ground to build the dam, out of the borrow pit, is compacted into the embankment. And now, there's nothing wrong with that kind of structure, provided that you've done the geotechnical investigation of the material that's available prior to construction, and that you've determined that this is a safe structure to build out of these materials. But if we say to people that the worst time to do your geotechnical investigation is while you're actually building the dam. It's a bit too late, and it's probably a fact that you've committed to a particular course of or a particular style of dam construction by that stage. And then the last one, which is generally what you get with larger dams or on a municipal scale, is where you've got a clay core and then you've got two outer zones which are made of a variety of materials, including rocks. And a lot of big municipal structures are created in that way. Now, we've got a whole design framework here, which Georgie and I have worked through there, and you can have a look at that in terms of how to build that, how to create a dam design, and Georgie in particular goes into some detail on all of that. What I wanted to go through now, though, was, just because it's perhaps a bit more important in some ways, is that the 24 steps to building a dam. You'll notice that there's a number of steps before we actually start building the dam. Now, a lot of people start building the dam by, they have a two-step process. One is ringing the earth mover, and the second is turning the engine on. Maybe there's a third step. Can it go there, please? And away it goes. And unfortunately, that's not the way to do it. And that's where you really throw the balls up in the air as far as risk is concerned. So us doing things the way we do start off with doing a site analysis, which is what we talked about last week, where we're looking at the prospective positions of dams in a landscape. And that takes us back even to the week before that, where we did some keyline analysis of the landscape, keyline geographic analysis. Next is, hopefully we've got a topographic survey that follows from all of that, and it may be that we need a more thorough topographic analysis of the dam site itself, and we can use drones and other technologies to help us with that. We definitely want to see how big the catchment is. And so, how big is the roof? I mean, it's when we're dealing with catchment work and dam building work, etc. It's very much like the landscape is a roof, the gutters on the roof are the water conservation channels, and the tank or the cistern is the dam. Now, there's no point making a cistern way bigger than the catchment of the roof. So again, it's that efficient application of capital that we want to get all of these things about right, so that we get a good amount of meshing between the factors of use. So we also want to know as I said before, want to do a geotechnical assessment. So you might say that each one of these is a yes/no point in the process. So especially when you get to catchment analysis, you might get to the point where you go, well, look, I just look at this site and there's no way, even if I put channels in, that I can get the amount of water that I need to this particular site. So you stop right there. And I've seen a number of sites over the years where people haven't done the catchment analysis and they wonder why their dam's empty, and they blame the earth mover. Right? They say, oh, my dam leaks. No, it doesn't. You don't have enough catchment. It's simple as that. So, and so on. So it's really important. The other part of it, which is part of the volume question, is that when you do the catchment analysis, you can, we had a showing of the movie last night, so I got to bed a bit later than I ordinarily will, even later than feather. Anyway, that's another story. One thing that the catchment analysis will reveal to you is what's called the peak flow volume. So as we talked about last week, that when you do a catchment analysis, you're looking at it from two perspectives. You're looking at the annual amount of water that's available to a site, off a roof or down a road or to a dam. But then you're also looking at what's called the peak flow volume. So this is the amount of volume that is coming to a site in an event. So you want to work out, do you every 10 years? What's that 1 in 50 event, or what's that 1 in 100, or what's that 1 in 10 event? Maybe you get 100 millimeters in 1 hour quite regularly, at least twice a year. And then you go, well, in every 5 years, we get 200 millimeters or 250 millimeters in an hour or in half a day or whatever it is. What's that going to equal in cubic meters per second of flow? And then that helps us to design how big an overflow that dam will need. Well, again, what are the prime causes of failure of small earth dams? Either the catchment's too small, or more regularly, it's because people haven't designed their spillway to be big enough. Now, just as an aside on that, I just thought of it then, I'll recommend to you a little article that I wrote. It's on our website. And if you go to, I think I'll just put over spillway. No, that's not it. I'll go to Southampton, I think. Here we go. When your overflow is too small. So I should have put, yeah. So this is a case of a client, Jeff Power, who's on Jeff and Michelle McManus, who got a property in Western Australia. And one of the things that happened there, I got there and I went, wow, they've got this dam that's down here. And they bought this dam, they bought this property, had this dam installed like people do. And the engineer had apparently designed this dam to have the right size spillway and everything. And anyway, I got there and I went, this can't be right. And so I did an analysis of the catchment and found that it's 5,800 hectares and the spillway is 3 meters wide. Now, even people who don't know that much about these things would sort of go, wow, that doesn't quite sound right. That's a really big area. So, yeah, it is. It's a huge area, actually. And so I worked out that the spillway, there's a couple of ways you can look at this. And I might have mentioned this before, so forgive me if I'm repeating myself. But one of the things that one way you can look at how big a spillway is if you're building a pond or a dam in a valley, is how wide is the valley itself? How wide is the cut of that valley? Because over time, that stream has been created by the volume of water that's flowed down it. So you can sort of look at it and go, well, I've got a little stream or a little valley, and you've got plenty around here, for example, or on your own properties, and you go, well, gee, it's 5 meters across. Well, it's probable, and I've seen this happen more often than not, that it's when you actually go and do the mathematics on how wide a spillway should be, it's generally about the same width as what the stream is already. Yeah, which shouldn't come under any surprise once you realise that. So you can certainly do that anyway. So I suggested a range of factors, but so this particular system gets in the order of 4,400 megalitres per year, and the dam is about 20 megalitres. So there's quite an amount of extra water. But yeah, so we had and this dam had actually gone over the top a few times, which is dangerous because, especially for people downstream, it's dangerous for you because what you've got is a structure that you're going to lose money on. And B, if you've got, imagine this is next to your boundary, and you've got a neighbour who's got a market garden just down from you, or some other system, and your dam breaches in a flood, and it goes down, and they get and all of the 100,000 cubic meters of earth that you've got in that embankment becomes a fluid mass and moves to their place. Think they're going to be happy? They might be. They might go, gee, this soil is much better than the shit I'm working with already. So they might be happy from that perspective, but they may not as well. So, yeah, so have a read through that if you're interested in that sort of thing as a bit of a case study where am I? As a case study. So then we look at, so the design, which I mentioned just a moment ago. So have a look at how you might do that. Discuss the objectives with all of the operatives. If there's a supervising engineer, but at the very least, if you're going to be the project manager, make sure you're clear on what you're going to do. Talk out with the contractors and any workers that you have on the site. Set the construction out, which is a relatively easy thing to do. Generally, there'll be 3 pegs that'll be, at a minimum of 3 pegs that'll be put out. There'll be the 2 at either side of the dam embankment, which mark the full embankment height. And then you'll have another one which will go back up the valley, if it's a valley dam, which will mark the full water height. And then off that, those pegs will be used for reference levels, so that as the dam is built, you'll get, generally those people use a laser level, and they'll do level checks as the dam embankment is getting built up. And you can cross-check then to make sure everything's level. Then you move the topsoil. So topsoil removal is something that's quite critical, and you do see a lot of old dams where the topsoil wasn't shifted, and so the dam leaks from the base. But topsoil needs to be moved to one side and placed out of the way of the general earthworks. If required, not always, but it's not always required, depending on the geotechnical investigation, you build a key trench, which is that trench which you would have seen in the diagrams before, which goes under the embankment. It's either directly under it or to the front of it if it's a diaphragm dam. And that stops any water seeping, because this area right here is a weak zone in a dam in a lot of soil types. And so water can seep in between the earth that hasn't been disturbed and the fill material that you've put on top. So a key trench which is packed full of pretty good clay acts to sort of suture that wound. The next thing that we do is, backfill all of that, is install a lock pipe, and there's a section in this chapter on lock pipe. So that's a pipe that's based at the bottom of a dam embankment, and where we can use the entire. It's like turning the dam into a tank, so you can physically empty the whole amount of water that's in the dam. So they're quite useful, and that's the time when you put that in, and then you start building the dam by excavating the borrow pit and moving that soil onto where the embankment is in 10 to 25 centimetre layers, and then gradually packing that material down with the tracks of the machine that's building the dam or some sort of roller. Again, that'll be something you'll assess as to what you need to do. You'll check as you build it up, you'll check the embankment levels correct, and that it's correct all the way across. And that you'll add a bit more, because there will always be a little settling of the embankment, which will vary according to the type of material it's being built out of. As we get up closer to the full embankment height, we might install a trickle pipe, and that'll be below the full water level. Now, the full water level will be determined by the spillway height or the overflow height. And the trickle pipe will allow those lower grade flows, those more general flows that come along, to be released from the dam, but instead of going through the earthen spillway, which makes it more prone to erosion as opposed to going through a plastic pipe. You might trim the whole structure now that you're up to the particular levels that you want, and then prepare. If you need to put a liner in, then you might look at doing that. And I'll just switch over to here for a moment to have a look at a liner. So I did have one in here. So this is And if anyone's interested in talking about liners more, we often use what's called bento liner. And a bento liner is a really great material. It's a sandwich of bentonite, which is sodium montmeliorite, in between two layers of geotextile. And unlike traditional butyl rubber liners or plastic liners, this actually gets buried. And it's a physical mineral barrier that'll last for a very long time, has a much longer life cycle than or duty life than plastic liners do, or polymer liners do, which are exposed to the sun, and of course that photodegrades them. The other good thing about these is they're about the same price as a polymer liner, and which is good. And finally, really good thing about them is that you can grow stuff on top of them. So as you can see, here's an example here where that's got a liner in it, and you can grow things. Whereas normally with a polymer liner, you can't grow anything on a polymer liner dam. So why would we do these? Well, you do these in situations where you've looked at the various costs, as we've done here. So one of the decisions, we did this in Hawaii, for example, and this site had extremely well-drained volcanic soils that they had plenty of clay, but it just didn't drain. The percolation rates were really high. And I know that in this region of northern New South Wales, there's a bit of that, where you've got red volcanic clays and they're just highly permeable, and they're really tough to get to seal. So let's say that you really need this pond because it drives a lot of your irrigation systems for your livestock or for your commercial agriculture, etc. So you look at it and go, all right, well, what are my options? And it's always the important thing to compare your options. So you might look at, in this case, we looked at building a tank from an ex-military tank. We looked at using poly fabric. We looked at using poly tanks. We looked at, and then we looked at using the bento liner, and we came to the point that the poly fabric and the bento liner had the best price per storage, per litre, per gallon, right? And that's what it ultimately came down to. And so we decided not, even though the poly fabric and the bento liner were the same price per litre, per gallon stored, the bento liner lasts, whereas the poly liner doesn't. So we thought this is a really good application of the capital there. Okay, what else have we got? So you might put the liner in, excavate the overflow, that's one of the final parts of the earthwork, and then cover the embankment with the previously removed topsoil. And if there's enough topsoil, then cover as much of it as possible of the whole excavated area. So we built a dam on our place a few years ago, but we'd done about 6 years of soil renovation prior to doing that. So ordinarily in our area, you only have just enough soil to cover the embankment topsoil. We had enough to put 1 foot, 30 centimetres of soil over the entire structure because we'd done the work prior. So there's certainly, not recommending that you wait necessarily 6 years before you build your dam, but you may not build all of them at once. And if you are, then you might want to consider renovating the soil on those areas, because the great thing about being able to cover the entire storage with topsoil is that generally the dam won't fill straight away, so you get a lot of grass growing on the topsoil. And then when you get the first lot of water coming into the dam, it's really clean. And also, when that soil is underwater, it's noisy under there because all of the life there's a lot of life that then resides in that soil. Whereas if it's just a hard, burnt brown clay or whatever, it's got subsoil, then there's no life in it. And of course, that means that there's a lack of aquatic life that will turn up and have a place and nutrients to gather from as well. So we recommend that you finish off the dam, because earth moving equipment is really expensive. It's $150 to $250 per hour or so. and it's not that good at finishing things off. And if you do try and do really good finishing with earth moving equipment, then you're going to watch those dollars fritter away really quickly. So we recommend that people get out there with a variety of tools. Quad bikes or side-by-sides are really good. Just get a big bit of concrete mesh and throw some logs on top of it or tires, and we use that as what we call a smudging tool, right? And so that will act like a really big rake, and because the concrete mesh is flexible, you know, the earth mover's made the basic shape. So that flexible, that's why it's good that we use tires on it often. It will shape to the contours of the shape but it'll smooth it all out. It'll take all the rough edges out and everything. And make sure that everywhere's covered that needs to be with topsoil. But also when you can't use something like that as a sort of a general smudge, then you get in with your rakes and your shovels and whatever else and just give things a bit of a finish. And then if it's clear that the topsoil is not going to have too much good growth out of it, like if it's very thin, then we recommend people get a general pasture mix with a mixture of species in it, of grasses, pasture seeds, and throw that over. And then a really good thing to do is to get some weather damaged hay or straw, which is a second option, because hay has seed in it, straw does not. So spread a bit of that out, and you only have to cover it very thinly, and then when it rains, that soil surface on the embankment is not going to be exposed, and you won't lose all of that topsoil, and you'll get much better chance of getting, because it's a litter layer, right? And so you get a much better chance of getting growth on the embankment, which will sustain. Then we fit any inlet and outlet valves to the lock pipe and fit any thrust blocks on the lock pipe as required, and install any rip-wrap or rock at the base of the trickle pipe and so on. So yeah, you can have a look through all of that. Now, we've only got a little bit of time to go. So you'll see there's stuff on designing your spillways and different ways to do that with level sill spillways or just straight normal return spillways. So there's a bit of information on the, again, ready reckoners so that you have some back of the envelope determinations on if you calculate your peak flow rate, your peak flood flow rate in meters per second, then from that we've got some tables here to tell you, depending on the slope, on the outlet slope, what sort of inlet and outlet width you should have on your spillways. So there's a bit of that sort of stuff in there. All right, what else did I want to deal with that was particularly pertinent for now? We had a bit of a chat we've talked a bit about tanks so far. One thing that a lot of people do is they miss, there's a really good principle which comes from landscape architecture, some of the people in California, in permaculture principle, which is called relative location. And relative location is probably most expressed in permaculture in the zone theory, but it's also in the relative positioning of different elements into a system. And so in this case, what we're looking at is the relative location of different built infrastructure into the environment so that we can, again, have as an outcome gravity. So a lot of people, when they build their properties from scratch, they'll often build a shed first, and they'll often move into it, and sometimes they'll never move out of it. But a lot of the time what you do see is that people have misplaced or mispositioned those bits of infrastructure. So it is not unusual, especially in Australia and the United States, particularly here in Australia, that the shed has a much bigger roof surface area than the house does, ultimately, because sheds are relatively cheap to build per square metre. And so I'd like people to think about the relative position of that shed in the scheme of things and try to get at least 8 metres of head above the house. Because that means then, because a lot of people don't want to clutter their house space or their building envelope with with a tank, right? So whereas when you've got a shed envelope, it's a lot easier to do that. So what we recommend is if you've got a shed, or if you're going to build a shed, put it up so that the bottom of the tank is at least 8 meters higher than the house. And that even goes further. I think I've got a diagram down further here where we're looking at fire prone landscapes. As you can see, there's a lot of stuff in this water chapter. There's fire. Not gone too far. Yeah, here. So you might look at a fire-prone landscape as being one where you have a lot more height than what you would ordinarily, and this is the. Sorry, I'll just turn that into 2 pages. That what you'll have. Oops. Go back. Is a situation where, the way, that you'll have maybe a tank on the top of the hill, which is not an unusual thing to have. So you're pumping from a supply up to there. If you're lucky, you've got a dam which might be of a height that's above your roof sprinklers. So in very fire-prone areas of Australia and elsewhere, we recommend that people put roof sprinklers on and all of those sorts of structures. And in that case, then the minimum head that you want, static head that you want, is 8 meters above the apex of the roof, not of the ground, right? So put it to you another way as well, that if you are looking to get a really good pressurized water supply, like I noticed this house here and the one up there that we're staying at this morning, every time you turn the tap on, what turns on? Pressure pump, right? And look at this, and we've got ample slope on this site. And so you sort of go, well, and there's a fact too that if you go down to some of the tank suppliers that you've got around here, and they'll give you a free pressure pump with your tank. You think, really nice people, give me a pressure pump with my tank. What an offer, right? No, what they've just done is they've just got a customer for life, because any engine that turns on, off, all the time, however many times you go flush the toilet, every time you turn it on, that's not an engine that's going to last for very long. So you'll be back for a nice little margin on your pressure pump, right? Whereas if you position these elements correctly, then you don't need that pressure pump at all. If you are going to have a pressure pump, here's the tip. Put them next to your guest house, because then your guests will only stay for about 2 days, which is about as long as you want them to anyway. Well, the guest room. So that's something to consider. If you're at about 8 meters of pressure, that might have to be a bit more, accounting for friction losses in pipes and all of the rest of it. If you're at 8 meters of pressure, you're getting about the same pressure as you're getting in town. So you can have a shower that wets you and stuff like that. So a lot of people, what they'll have is they'll have a tank, a header tank, which is just it's just not high enough. And so you turn a shower on and it's kind of unfulfilling. So or it takes just, you go to fill your kettle up, or you walk outside and have your cup of tea and your kettle's full by the time you've had you're ready for your next cup of tea, right? So yeah, important to do all that sort of thing. All right. The other thing I wanted to deal with before we wind up and take any questions that people might have is, where is it? Is irrigation itself. So I might just shift over to the presentation-y bit of this. So one of the systems that I'm a big fan of is the K-line system. Now, what this means, and I was talking to Joel, I had a two-hour conversation with Joel Salatin the other morning, because we were talking about a new program that we're doing, and I introduced him to the K-line system years ago, and so he's got it at Polyface Farm now. And he was raving about it. He's just saying, "Oh, how great this system is!" Blah blah blah. And he was confused because he was saying, "Is it K-line or keyline?" I said, "No, Joel, it's a K-line system. It's K-line irrigation within your keyline irrigation network," which it is, and the cheeky Kiwis, of course, trying to confuse us. But no, this is a really good system. What it does is, well, why I like it in particular is that it uses water. It uses a lot less water, so it uses a lot less water to go a lot further. So in traditional flood irrigation, which is what P.A. Yeomans announced to us all and has been used for a long time, it's a very water expensive system, whereas K-line irrigation and more sprinkler-based systems use water much, much more effectively. What they do as well, so for example, the K-line system puts water out at around about the rate of 3 to 6 millimeters per hour. So imagine you call up your God, or you're just call to the sky and you say, "Oh, I've been such a good person. Can you bring me a really nice rain? I'd love to have 6.25 millimeters of rain per hour for the next 3 hours. Thank you." Maybe you can, you just turn it on, right? So whereas with a lot of other systems, like with flood irrigation, really hard to modulate that amount of water out onto a system. And you just end up, so what you end up doing is, as Yeomans did, because that was the technology that he had for distributing water back then, it was he had to build really big dams. And really big dams cost a really big amount of money. They take up a lot of space, and they may put you in trouble with the authorities, right? So whereas what we suggest to people is understand. So if we recap, go back to the top and understand what the amount of water that you need. Try and do your best so that you can cover as much of your soil as possible, so you infiltrate as much as you can, and so that you need, try and build soil carbon as your first irrigation strategy, right? So do that so that you're getting rainfall as effective as possible, and then pipe everything else. And by piping water, you save an enormous amount of water just by piping. And then once you pipe that water, particularly for livestock systems, then all of those dams that you had in the system that used to be the dam that the animals drank from are now redundant. And so you now fill them back in, or turn them into some sort of wetland, or use the water from them for another purpose, like irrigation, right? Which means now that off a smaller acreage, you can leverage the water resources that were redundant for drinking water, so to speak. They improve in their quality, and now you can remobilize them for other purposes, and of course then increase your production and resilience overall. So that's something that we do talk to people about. The biggest issue with that kind of process, however, is that you may need to, because you do in a lot of parts of the world, and definitely here in Australia, you need to buy access to irrigation water. You can't just necessarily use it. You have to buy it, and that can be a problem, particularly in the Murray-Darling Basin and in other catchment basins where the amount of water is actually fixed. The amount of available water for irrigation is fixed. So you have to wait for someone to die, or you have to wait, or you have to buy their water or something like that. You have to buy the water. That can be a pain. So the good thing about K-line is it fits in with your normal system of reticulation. So use that permaculture principle of each element performs multiple functions. Well, now your water pipe reticulation is not just supplying your stock water with a flexible irrigation system, but it's also supplying irrigation water. And with that, and this is a good example of Ben Falloon, an old client of ours at Taranaki Farm, we set up all of this years ago, and he irrigated, and he did a study which I found interesting, that he analysed the amount of water that he put out, and he got in trouble with his neighbours and with the water authority, because he hadn't actually bought any water, and he's in an area where you need to buy the water to irrigate it. So he got in trouble, and I said, and he was carrying on, and I said to him, well, "Why don't you buy a water right?" And he said, "Oh, it's too much." I said, "Is it?" And I said, "Have you thought that through?" And he said, "Well, no." I said, "All right, well, let's do the math on it." And I said, "Didn't you just do a post the other day showing how you just bought in all this extra feed? Rolls and rolls and rolls, a semi-trailer of feed that you bought in, of hay bales." He said, "Yep, all right, how much did they cost?" "Right, well, there's our benchmark." So what we did was then a calculation based on the volume of extra feed that he was able to grow using this irrigation water, because the irrigation water had $1,000 per megalitre cost, right? How much feed can you grow for 1,000 megalitres? And what's therefore the cost of that feed versus the cost of that feed coming in on a truck? Yeah, no brainer. Actually, it was about 1/10 the cost of the feed. So, yeah. So, sometimes, people don't work things out. And so, of course, you make assumptions, and you just make an ass of you and me, as they say. So, lots more to cover, of course, in terms of stock water, and, if you're going to do earthworks, make sure that they're covered. This is at Teresa, who's here. This is her father's property. So I did a channel one day, and we rolled out some hay on top of that, and hey presto, a month later, nice green channel, just with a few rolls of old shitty hay. Using pipe layers to bury pipe and all sorts of things like that. Using having different stock water irrigation systems. I did have something on that here. So where we're using hydrant-based systems to reticulate water around a property. I have an example plan of that here, where this property's in central New South Wales, about 800 acres, where I've designed a system of water reticulation which fits in with the fencing. And so for those of you who are interested in setting up a bit of a water plan over the coming weeks, you might want to look at a template like this, where I've set up, as we talk about, I've set up the Google Earth template, so that it follows the Agrarians platform. You've got existing and proposed dams and so on. So if we just look at the pipe systems, there's a lot of dams on this property. Most of them are now going to be redundant, apart from a couple. So there was one, what was it, up here? So dam 7. This one here we were proposing to enlarge, and from it we were going to pump up to a tank on the highest part of this property, of this section of the property. And from that, of course, because you can do this, and this is where you can use your Google Earth quite cleverly. I've got tank 1. I'll just I'll send you. I'll put a copy of this particular plan on the workplace as a template for you. But what I did here was speculated for this amount of area, different kinds of different sizes of tanks that we would use. And how many days water they would give for the amount of grazing days, perceived grazing days that we'd have in that area. So and then looked at the cost per litre for those tanks. So as the larger you go with the tanks, then the less cost they have per litre of storage, and so on. That's that one. I did another tank over here for another part of the property. So we're pumping from an existing dam up to another one, and then reticulating that around. The H code is to do with hydrants. So click on that, get info. So that's a hydrant, and that ties into a bill of quantities that we've got, which I think I'll make a note to share as well. for this particular design or plan. And so pipe 7, which this is part of, has a number of hydrants. So pipe 7 requires, it's 40 millimeters in diameter. We need 157 meter rolls. It's 1,070 meters long. We need 7 hydrants, and they're all placed at 150 meter spacings on the. So we're using threaded tees with a cam lock fitting placed into those. With a little ball valve, with a little gate valve. So they're all. So that's an example of how we've meshed in, as we've talked together with the layers, where we've meshed in the fencing layer with the water pipe layer, and then that allows us to have a full reticulation of water by gravity around this grazing property. Yeah, at a cost for this particular property, which was I think 780 acres or so. I think the cost was about $80,000 or $90,000 for the whole property. That included all the dams and tanks and pumps and so on. So it was a relatively low cost for the kind of operation, given that that investment would effectively in the first 2 years double the carrying capacity of that property, which with cattle grazing in itself would more than cover the cost of the infrastructure in the first or second year. So that's a pretty good return on investment. Now that's not always going to be the case, but in this case it was. All right, we've got Q&A, so I'll just get back to some of the questions that we've got hanging there, and also, anyone here got any supplementary questions before you go out and Danny cracks the whip and gets you out and about? Yeah, all asleep. Good. Yeah, righto. Thomas, can I explain the reconstitution zone, what that means and what it's primarily used for? So if we go back to the handbook there, because I think that might have been a section that you missed out on because I was remiss in not turning the vital screen share bloody button on. All right, here we are. So the reconstitution zone is, Thomas, what would it be used for? Well, it would depend on what depends on your attitude, I suppose. I would look at it as being, well, I'll go back. If we look at when Alan Savory is asked, what is the determinant of the quality of land use? He said, well, one determinant is how clean is the water that leaves your property, right? So you've got the water comes in. Let's say you've got a stream that's running through your property. That water comes in a particular quality and leaves in a particular quality. Now, the quality it leaves on is largely going to be an outcome of your management. So if I was looking at this, I would look at the landscape to start with and see what value it had from a production capacity. But let's say it doesn't have very much. Let's say it's wet all the time. I would just turn it into wetland. And, that's basically the livers and kidneys of the planet, of your property. And so that will clean the water before you leave it. And then, of course, you'll put because you're involved in, and I think we did talk about this actually, because you're involved in getting payments for ecosystem services, you're now getting a payment for cleaning up the water because your municipality is really interested in having clean water, and they're paying you a payment for that, and that does happen. So, but as a good citizen, it's a good thing to do to make sure that the water that leaves your property is in a better condition than when it came. Right. So that's what that's primarily used for. Blair's saying, while you're here, can you come and fix my dam? Well, I don't know about that, Blair. I might be able to point a finger at it. I know we are going to catch up, so I'll come and see what I can. I'll see what I can do. Fix it. I think you'll have to fix it. I'll just point the finger about how you might fix it. So thanks for that, mate. What else have we got? Deal, right? He's quick on the deal, right? Quick on the button. The rest of them aren't seeing anything. Yeah, can't see. Oh my God, I can't believe I did that. Anyway, can't do much about it now. Any other questions that anyone's got from the workplace at all? Okay. Nothing in the chat. No. Okay. All right. Well, I'd like to thank you all. We've obviously got a lot more to cover on this, and I'd probably need to do a whole day to cover everything that I've just got in the handbook. Can I just remind you that the location of the handbook for the planner subscribers, just so you know where that is. I'll just go back to here. It's in. So if you go, so this presentation is in the presentations. You'll go to here and you've got the RHB chapters 1 to 3. So please do as I've done. Go down to your local Staples, Officeworks, Office Depot, any of those places, and print one of these out so that you've got it. Makes it a lot easier to navigate. It was designed to be printed. And have a good read of that. I'll be back on this today and this evening. I'm doing a bit of survey work today, so I'll be working this evening on the workplace. So yeah, thank you very much, and thank you also to our friends here for hosting us and inviting us up here. There they are. There you all are, watching the big screen, and we look forward to all of your questions and task work coming through in the coming days. So with that, I'm going to sign off and wish you all the best. And in the meantime as well, I forgot to say, I'll look to get that first part of the program. I'll just have a look and see if the recording, because I need to make sure that the recording works with the screen being recorded. Because I'm not sure if that worked, but if it didn't, then I'll certainly be happy to re-record, and I'll schedule that in the next couple of days. All right, and it'll either be tomorrow or Thursday. Apologies again, and have a great day. Thank you.